Welcome back. In this episode, we zoom out and look at the big picture of weather, global climatology. This is about long-term patterns in wind, temperature, and pressure that shape the environment we fly through. Let's explore how Earth's climate zones and circulation systems affect aviation worldwide. Let's start with the basics. Climate refers to the average weather patterns in a region over time, not just a single day or storm. It helps us understand seasonal weather and long-term wind systems. Earth has three main climate zones based on latitude. Tropical, 0 to 30 degrees. Temperate, 30 to 60 degrees. Polar, 60 to 90 degrees. Each zone has unique weather features that impact aviation in different ways. In the tropical zone, temperatures are consistently warm. You'll find rising air near the equator, known as the Intertropical Convergence Zone, ITCZ. This zone is packed with thunderstorms and convective activity, a major consideration for long-haul flights. The temperate zones experience changing seasons, with both frontal systems and jet streams. These mid-latitudes are home to depressions, anticyclones, and the majority of weather variation pilots must track day to day. The polar zones are cold and dry, with stable air and low precipitation. However, low-level jet streams, icing risks, and limited daylight make Arctic operations especially challenging for flight planning. Let's now talk about global wind circulation. Earth's rotation and solar heating create three main cells per hemisphere. Hadley cell. Ferrel cell. Polar cell. These drive large-scale wind patterns and influence weather systems worldwide. In the Hadley cell, warm equatorial air rises and moves poleward before descending at around 30 degrees latitude. This creates the trade winds important for planning routes across tropical oceans. The Ferrel cell lies between 30 degrees and 60 degrees latitude. It's where we find the westerlies, winds that blow from the west and affect many transatlantic and transpacific routes. Jet streams also flow here, guiding storm systems. The polar cell circulates cold air around the poles. Winds flow outward from the high-pressure polar centers. Although weaker than tropical systems, these winds influence Arctic flight corridors and airspace management. Now let's look at pressure belts. The equatorial low is a zone of rising air and frequent thunderstorms. The subtropical high around 30 degrees brings stable, dry conditions, think deserts. The subpolar low around 60 degrees is a breeding ground for mid-latitude cyclones. The polar high features descending air and clear skies, but can also bring bitter cold. These belts shift seasonally, affecting where storms form and how wind systems evolve. For example, the ITCZ shifts northward in the northern hemisphere summer, bringing wet and stormy conditions to areas like West Africa and India. Let's take a practical case. You're flying from Sao Paulo to Dakar. Your route crosses the ITCZ. Expect CBS, turbulence, and wind shear near the equator. Flight crews often plan for altitude changes or reroutes to avoid the worst cells. Now let's touch on climatic effects on airports. In equatorial regions, expect afternoon thunderstorms and poor visibility. In desert climates, turbulence and density altitude issues. In temperate areas, frequent frontal systems and wind shifts. In polar regions, extreme cold, frost, and navigation limitations. Understanding climate zones also helps when selecting alternates. If your destination is affected by monsoon weather, look for alternates in different climate zones for more stable conditions. Let's also talk about seasonal wind systems. Monsoons bring seasonal rain and wind reversals, especially in Asia. Trade winds blow consistently east to west in the tropics. Jet streams shift with the seasons, affecting flight time and turbulence. For example, winter flights from Europe to North America may face strong headwinds, while return flights catch the jet stream for shorter routes and fuel savings. Airlines plan routes based on these seasonal wind patterns. Another useful concept is climate variability. Even in stable zones, El Niño and La Niña events can disrupt normal conditions. These oceanic cycles shift wind, rainfall, and storm activity worldwide, important for long-haul and seasonal ops. Let's wrap up with why global climatology matters. It explains long-term wind and weather patterns. Helps plan seasonal flight routes. influences airport performance and alternate selection, informs us of recurring weather risks in different latitudes. In the next episode, we'll continue with global climatology, part 2, where we'll explore real-world flight routes, jet stream effects, and how climate patterns affect international aviation planning. See you in Meteorology number 43, Global Climatology, part 2.